In the name of the Almighty, the Compassionate, the Merciful. Again, we come to the end of our series of lectures concerning the methods for calculating antiderivatives. This one, in fact, is our last lesson concerning this topic, how to calculate antiderivatives. And we said actually there are a few, something like 5 methods. And these methods begin with the method of substitution. Then if this doesn't work, the most powerful, we said, the method of integration by parts. And then we moved to, we said that if your function is only composed of trigonometric or alone or hyperbolic functions alone, then you may use some sort of kind of methods which purports to the powers of the sine or the tan or the sec, etc., which is much simpler. And then our last lesson, which we talked about the method for removing square roots and radicals, etc. And now this is our last lesson concerning the ways for calculating antiderivative, which is called partial fraction integration by partial fractions. So in this lesson, we are going to speak about what the partial fraction representation of a rational function, and then the linear versus the quadratic terms. When do we obtain linear either or quadratic terms? And then we will speak about simple ways for calculating derivative, for calculating coefficients of these what we call partial fractions. And then we shall move to speaking about some integrals. Partial fractions, in fact, are the methods which one uses in order to simplify a rational function of this sort. It's a polynomial divided by another polynomial. Here you have p of x divided by q of x. And it's immaterial what is the degree of p or what is the degree of q, etc. But if you can decompose q into brackets of linear forms or linear brackets or quadratic brackets, then you may transform this rational function into what we call an addition or a sum of partial fractions. So in fact, what we do, for example, suppose we have an integral of the sort, the integral of 1 over x times x plus 1. What we do is that we transform this function into 1 over x minus 1 over x plus 1. This is how it is done. Of course, you need not use the theory, but it's simple. You know, you watch out for your brackets in the denominator. It's x times x plus 1. So you must have here a common denominator. So it must be something over x minus something over x plus 1. Why minus? Instead, because if you try to take a common denominator, then the x must cancel out with the x. So here x plus 1 minus x, you get 1. So this is the form which is transformed from 1 over x plus multiplied by x plus 1. And the integral here becomes very simple, because the integral of 1 over x, the antiderivative is ln x, while here it's ln x plus 1. Of course, you may, as I said before, you may leave it this way, or you may put the modulus if you are considering definite integrals. And then here you may also wish to put it in a form which is which only looks like a little bit beautiful. That's all. And this is your antiderivative of your original function. So actually what you did is, in fact, you transformed your function, which is a rational function, into the form of two partial fractions. Here, this is the first one, which is 1 over x, and it's a linear polynomial in x, and this is one also, it's a linear one. Because why? Because your denominator here can be decomposed into linear forms. But suppose you have a polynomial, you have qx, which is rather long polynomial of degree higher than, for example, 2 or 3. Suppose you can decompose it. What form of decomposition can qx have? Qx, it can have either linear or quadratic forms. Why? Because it cannot have, because since we are only considering coefficients of q of x which is all real, then you cannot end up with, for example, degree 3. If you have a degree 3, then it must have, if you have a degree 3, we said before that it has either one root or 3 roots. Because if it has complex roots, it must appear in conjugate pairs in order that the coefficients are real. If they are not in conjugate pairs, these complex roots, then you may not end up with a real sort of coefficients. These are the one that we have in our topic here. The coefficient must be real, and therefore, if you multiply x, x minus a minus j, which is square root of minus 1 b, you multiply it by x minus a plus also j b, you end up with a real with a polynomial which is real. So you have to have the roots in conjugate pairs in order to have you have a real coefficients, and therefore you end up with what? Since you have only two roots, they add up to x minus a all square plus b square, so you always end up with what? With either linear factor or factor which are quadratic. And what you do is that you wish to determine these partial fractions, h1, h2 till hr. These are called partial fractions, and they adhere to certain rules. The rules are the following. First of all, you have to notice that the degree of p of x must be less than the degree of q of x. If the degree of p of x is higher than that of the denominator, they have to do long division. Long division until you are sure that the degree of p of x is less than, not equal, less than q of x. And from then on, you can proceed to determine your partial fraction, but not before. We use long division to obtain a polynomial plus a remainder. Of course, this remainder is could be R, a polynomial. You divide them both, and you get a remainder divided by q of x, and this remainder has a degree less than q of x, and therefore you can decompose or transform your R of x divided by q of x in the form of partial fractions. Suppose q of x is the product of polynomials of this sort. Either they are linear, I said before, either they are linear or quadratic. They can't be of third degree, because the third degree polynomial, if you equate it to 0, you get an equation which has one real root and either two conjugate roots, complex, or three roots which are real. So either your three order polynomial can be decomposed into three linear factors, or one linear and the other one is quadratic. So finally, eventually, you have either linear factors or quadratic factors. Of course, you may have factors of this form. If you have, for example, double roots, factors of this form, it doesn't matter. But so long as you have either linear or quadratic, it's okay. And then, suppose all the terms are linear. So in other words, q of x is in this form. Here you have a1x plus b1 times a2x plus b2. In other words, you have so many roots. You have n minus 1 roots of the form bi over a minus br over ai times at the end, and you have one which is a double root or n time roots of equal to minus b over a. So how would you put your partial fraction in which form? Your partial fraction in which case will be in this form here. First, the single roots are your partial fraction look like form addition sum of fractions of the form constant a1 divided by a1x plus b1 plus another constant a2 divided by a2x plus b2. Of course, we know very well that we are given p of x over q of x, and we wish to calculate the a's which are the coefficients until you end up with the r root, which is ar x plus br, which times when you have denominator ar, which is again a constant to be determined later. And then for the root, which is multiple root of order n, what you do, you have a prime divided by x plus b until you have n. Here it means that you have n roots equal to minus b over a, and this is the form how you go along with and you wish to calculate your a's and your a primes. On the contrary, if quadratic forms appear of this sort, again they can be of this form. And nothing else. You have a1x squared plus b1x plus c1 times a2x squared, etc. Of course, you may have both together. You may have a linear term added to multiplied by a product multiplied by a quadratic term. It doesn't matter. It's all the same. So you end up with what? You end up with quadratic terms, and you may have a quadratic term of multiple multiple of one another. In other words, you have a quadratic form of the power of n. So your partial fractions will take this form here. P over x over q of x will look like this. You have the ones which are simple. You have a1x plus b1. Why a1x plus b1? Because this is how the theory goes. It tells you if this is quadratic, if your denominator is quadratic, then your numerator must be a linear form. So here again, a1 and b1 are unknown, and they are later determined, and etc. up till you have your final or the one before final quadratic form here, and again you have to determine AR and BR. But for the one which is multiple of n, you have to have it in this form. You have to have in the form which is similar exact to the one which is linear, except that you have to have a1 prime x plus b1, a linear form, and again a1 prime, b1 prime, a2 prime, etc. b2 prime have to be all determined. Suppose, for example, we wish to calculate, integrate this fraction here. So what we do, we start by the denominator. Well, the denominator is, of course, of the form x cubed, it's a polynomial, 2x squared minus x minus 2. First, we have to calculate the roots. Of course, to calculate roots of third degree is difficult. Second degree, we know there is the discriminant, this form of which is every student know from school. But if it is third degree, then it's more difficult, and we have to resort to some numerical techniques. In the old days, we used to teach method of Cardan and Ferrari, which Italian, which concern the calculation of roots of third and even fourth degree. Up till, of course, after 5, before 5 and etc., we can't, according to Galois and Abel. But in any way, there are rules, there are numerical techniques, and this is why we give up these methods to calculate them. But suppose, for example, we have a simple one like this, and we wish to test to calculate the roots. For example, we wish to suppose that there is a root x is equal to 1. Would this work out? 1 plus 2 minus 1 minus 2. Yes, actually it is equal to 0. So this is a root. So what about the rest of the roots? There is actually a simple method which is due to some scientist called Kashi, a Persian one of the Arabic culture in the 14th century. But this is called Horner rule. In the West, it's called Horner rule. What you do is that you work out, you write the coefficient. Here, a coefficient of x cubed is 1, of x squared is 2, of x is equal to minus 1, and the constant term is equal to minus 2. And what you do, you have this table. You suppose, for example, that 1 is a root. You know that 1 is a root. Is 1 is a root, how would you go for the other roots? How would you calculate the other roots? What you do is that you lower the first coefficient. You write here 1. The same, and then you multiply 1 by this root. 1 by 1, 1 times 1, it gives you 1. And then you add up. Again, you write down all the coefficients of your polynomial, which you seek to calculate the roots. And then you write your supposed root. You find out that 1, for example, works. And then you write your root here. And then your 1, the first coefficient, you write it down as it is. And then you multiply the first coefficient by your root. It gives you 1. You add up, it gives you 3. And then you multiply again, 3 by 1. 3 times 1, you get 3. You add up, it gets 2. And then 2 times 1, you have 3. And then you add up here, you have 0. If you have 0, it means that correct, that 1 is the root, since you have no rests. And the remaining polynomial is x squared plus 3x plus 2. Of course, you can move along to calculate the remaining of the root, because here directly is x plus 2 times x plus 1. And these are the remaining, the decomposition directly of your polynomial. So in fact, your polynomial is what? Is in the form of 3 brackets, x plus 2 times x plus 1 times x minus 1. Or you may, of course, proceed. If you proceed here and you for example, check that you wish to check whether x minus 1 is a root, so you put here instead of 0, you put minus 1. And if you put minus 1, you will find out that it works as well. 1 minus 1 gives you minus 1. You add up, you get 2. You multiply again, you get minus 2. And minus 2, you add up, you get 0. So again, you end up with x plus 2. And thereon, you can calculate the rest of the roots. So in fact, your polynomial here would be decomposed into x plus 1 times x minus 1 times x plus 2. This is your q. You know now that your q is in this form. So this fraction in fact can be put in the form a divided by x plus 1, since they are all simple, plus b b divided by x minus 1 plus c divided by x plus 2. And then you move onward to calculate a, b, and c. Because once you calculate a, b, and c, you can integrate one by one, and these are all logarithmic, the antiderivative are all logarithmic functions. So here we decompose it, we found it in the form of these three brackets, and then we obtain your rational function in the form of partial fraction of this form. Now you wish to calculate A1, A2, A3. How would you go for calculating these constants? There is actually one simple way of doing it. You can equate the numerator of both sides. You can have x squared plus x plus 4 is equal to what? Is equal to A1 times x plus 1 times x plus 2 plus A2 times x minus 1 times x plus 2, again finally plus a3 times here, in which case there are a1, a2, and a3. And a3 times x minus 1 times x plus 1. And then what you do, you equate the coefficients of equals powers of x. So for example here, for powers of x square, you have 1. Here you have what? a1 plus a2 plus a3. And this is how it, here the polynomial, you equate the numerator with the denominator, with the numerator of your partial fractions. So you have the coefficients of x squared is equal to 1. What about the coefficient of x? Here you don't have x, but here you have what? You have a2, and here you have 3a1. So that's it, that's the coefficient of x. When you equate, you get three unknown, and you solve them to calculate, to obtain a1, a2, a3. In fact, there is a simpler way of doing this as well. What you can do is that you write this in the form a1 divided by x plus 1 plus a2 divided by x minus 1 plus a3 divided by x plus 2. And you wish to calculate, if we go back to our polynomial, which is x squared plus x plus 4 divided again here by x plus 1 times x plus minus 1 times x plus 2. Suppose we wish now to calculate the coefficients a1, a2, a3, and wish to solve them. Suppose now we obtain a1 to obtain a1. What we do is that we multiplied both left and right hand side by x plus 1. And then we substitute x is equal to minus 1. Why? Because when you multiply this by x plus 1, this disappears. You have a1 only. Here you have what? a2 times x plus 1 divided by x minus 1. So when you put x is equal to minus 1, it cancels out. Here again, if you multiply this by x plus 1 and you substitute x is equal to minus 1, cancels out again. So there remains here what? This, if you multiply this by x plus 1, as if you are hiding actually x plus 1. When you hide x plus 1, you are left out with this fraction here, and here you have what? You have a1 plus a2 times x plus 1 divided by x minus 1 times a3 x plus 1 divided by x plus 2. So when you substitute x is equal to minus 1, this cancels out, and as if here we are hiding x plus 1, and then you substitute here x is equal to minus 1. If you do this, we get what? Minus 1 plus 1, they cancel out. 4 divided by minus 1, you get minus 2, multiply by 1, so you get a1 is equal to minus 2. Is it the case? a1 is equal to minus 2? No, we did a mistake. So we have to go back again and check out for a1. You wish to calculate a1. So what we do is that here cancels out, and here you put x is equal to minus 1. See here you get 1 minus 1 plus 4, correct? And here you put x is equal to minus 1. So you get 1, and minus 1 you get minus 2. So you must have a1 is equal to minus 2. In fact, apparently, this is a2. Because yes, that's it. Because in fact, what we did is that I wrote it in a different way, but it's immaterial because your a1 is a2. Same thing here. The coefficient. What I'm seeking is the coefficient of x plus 1. So in fact, this I'm seeking to obtain a2. Whereas if you want to obtain a2, which in this case here it's a1, you multiply by x minus 1, and you set x is equal to 1. So you have a2. In my paper, in other words, a1 in the slide. So you set x is equal to 1. So you get what? You get 1 plus 1 plus 1, 6. Divided, you put here x is equal to 1. You have 3. And you multiply by what? X is equal to 2. So in fact, a2 is equal to 1. Is a2 is equal to 1? In other words, is a1 is equal to 1? Yes, that's true. So in fact, this is the way how we do it. This is, in fact, simpler method than equating coefficient, but they both work out simply. Of course, if there are multiple, then you may differentiate, or you may multiply by the multiple of the bracket, etc. But this is actually a simpler way of doing it. You hide a bracket, and then you substitute for the root of the bracket which concerns the coefficient which you seek to calculate. Thus, the integral at the end finally is going to be, the partial fractions are in fact a1 divided by x minus 1 minus plus a2, which is minus 2, plus a3, which is equal to 2. And you end up with what? With the integrals of the original, the integral to which you calculate. You want the antiderivative of your fraction. It's equal to the sum of the three integrals. The first one is ln mod x minus 1. The second one is minus 2 log ln x plus 1. And the final one is 2 ln x plus 2. And this is how it is done. Evaluate this integral. This integral actually have one root as 1 and two roots as minus 1. So your theory tells you that if you have a double root, then you must have your fraction in the form of a1 divided by x minus 1. But for x1 plus 2 square, you must have it as a2 times x divided by x plus 1 plus a3 divided by x plus 1 square. And you move forward with the same thing. You move forward to equate coefficients. If you equate the three coefficients, it's simple. You don't have to waste time doing this. You have three equations and three unknowns for the coefficient, and you got directly the three coefficients. One of them is 0, meaning that the coefficient of x plus 1 does not appear. So you end up with 1 with x divided by x minus 1, another one for x plus 1 square. Of course, the integral of this is a ln, whereas the integral of 1 divided by x plus 1 square is minus 1 over x plus 1, and you have minus here. So this is the final result. Suppose you have an integral of this sort. This one here, we cannot decompose into partial fraction. Why? Because the degree of the numerator is higher by 1. So we have to divide first the numerator by the denominator. So you have here x squared plus 2x plus 1. When you divide long division, you have here x. So you get x cubed plus 2x squared plus x. You subtract, you get minus 2x squared plus x. Minus 1, and here you get minus 2, and you have minus 2x squared minus 4x minus 2. You subtract again, you had 5x plus 1. So in fact, your fraction becomes what? Becomes x minus 2 plus 5x plus 1 divided by x squared plus 2x plus 1. Of course, this is equal to x plus 1 squared. So you have to divide first the numerator by the denominator, because the degree, yes, that's it. The degree of the numerator is higher by 1. If it's higher by 2, doesn't matter, or higher by 3. But you have to do long division until you end up with a fraction of the degree of numerator less than that of the denominator. And from there on, you move forward with your partial fractions. Here, because you have two roots, so it must be of the form of a divided by x plus 1 plus b divided by x plus 1 square. Of course, it's simple that you have it in this form. Why? Because if you multiply by x plus 1 square and you let x is equal to minus 1, you get 5 times minus 1 minus 4 minus 5 plus 1, which is minus 4. So you have this coefficient directly. And the other one you need not to, of course, because you can equate having common numerator. So you must have here 5x plus 1 minus 4 to end up with 5x plus 1. So in fact, this is the final form, and the integral of this is straightforward. That's it. This is the integral directly. All these integrals, x gives x squared by 2, etc. And this is logarithm, and this is 4 over x plus 1. Evaluate sine x divided by cosine square plus 4x cosine square cosine x minus 5. This is, in fact, is a kind of trigonometric integrals, but of the form which can be managed to transform into a rational function. Suppose you take cosine x is equal to u. If you take cosine x equal to u, this is the substitution that you do, then you have minus sine x dx is equal to du. So in fact, the numerator here is equal to minus du, while the denominator becomes what? U squared plus 4u minus 5. In other words, it's a rational function. When it is in the form of a rational function, it's straightforward. You have to decompose it in what? You have to find the root. The root is what? The brackets here, or the linear form, are either it's equal to u plus 5 times u minus 1. So it must be in the form of here you have 1 divided by u squared plus 4u minus 5. It must be, in other words, x u plus 5 times u minus 1. So it must be in the form something over u plus 5. You need not go into partial fraction expansion. This is stupid. It's directly, it must be of this form. Why? Because you have to cancel out the u in the numerator. So if this is u, this must be minus 1 here. In order to cancel out, when you take common numerator, u minus 1 minus u, you get here, you only get in the numerator minus 1 minus 5. So all you have to do is you divide by minus 1 over 6 in order to finally obtain 1 over u plus 5 times u minus 1. And since you have here negative, so you end up with a positive 1 over 6. And finally, the integral of this two forms, you need not, as I said here, remark, for these simple trivial fractions, rational functions, you directly write them down in the form of two rational two fractions in the form of linear forms, and you make sure that when they multiply together as to obtain a common numerator, you end up with a constant, and you divide by this constant in order to obtain the partial fractions. And again, the integral of this is ln u plus 5, and the other integral ln u minus 1. Since they are subtracted from one another, you can use algebra to divide both logarithm. To subtract both logarithm. In other words, you divide both linear forms, and this is again your antiderivative. And finally, you substitute for u. You already have u is equal to cosine. This is substitution. So you substitute back for u is equal to cosine, and you end up with your result, which is the antiderivative of the integral which you seek to calculate. It. Integrals of this form, when you have, for example, sine, of course you can do them with half the angle, the one that you saw in our last lecture, but you can do it in a simpler form. When you have integral of the form b sine ax plus c cosine ax, what you can do is that you can construct a triangle in which, for example, this is b and this is c and this is the square root of b squared plus c squared. So this integral, in fact, boils down to what? It is reduced into b. You multiply first. You have to multiply first by what? You have to multiply by 1 over the square root of b squared plus c squared. So you have here b divided by the square root of b squared plus c squared times sine ax. Plus c divided by the square root of b squared plus c squared times cosine ax dx. So in fact, it is going to be reduced to b squared plus c squared. The integral of what? Since b divided by the square root of b squared plus c squared is equal to the sine of this angle. Suppose the angle is phi. This is constant. So this is cosine of phi. So you have this is the sine. So in fact, you have what? You have an expression which is sine x cosine phi plus cosine x sine phi. So in fact, it is what? It is sine ax plus phi, where phi is here constant, and here you have dx, and you moved forward the integral of 1 over sine, which is cosec. We know the integral of the cosec, which is logarithm cosec minus cotangent. So actually, this is one way of doing it, better than the half angle substitution. So integral of this sort can be managed in this way, like we did here. You construct a triangle in which you can perform some algebraic manipulations to put in the form of an expression of sine something plus a constant. Now we have some other integrals. These actually, since we are finishing the antiderivatives of studying antiderivatives of functions, you may have, for example, integral of this sort. Here you are confused what kind of substitution you do. For example, you may take, for example, u is equal to the 4th root of x cubed plus 4. If you, which actually it doesn't come into the mind of some students, neither to myself. This has to be done through your experience in, and this is actually one disadvantage of integrals. Antiderivatives, calculating antiderivatives is much more difficult than calculating derivatives. Derivatives are straightforward, but antiderivatives you have to actually gain some experience, and the more you perform integrals, the more you acquire this experience. So if you take a substitution of this sort, you end up with actually solving this integral. Integral of this sort, when you have, for example, square root of x plus 1 divided by x plus 2. Integrals of this sort, this kind of integrals, in fact, first of all, we have to make sure that the integral exists. So this function, as a matter of fact, we have to find a domain or an interval in which there is some antiderivative for this function. And in fact, here directly under the square root must be positive, and we said this in our 3rd lecture when we studied functions and domain of functions. So either you have x greater than or equal to minus 1, or x less than or equal to minus 2, in order that this becomes positive. How to move onward to calculating this antiderivative here? you can in fact, for example, multiply here your condition. For example, you may take x greater than equal to minus 1. Of course, you may take also x less than equal to minus 2. But if we chose this substitution, this condition here, in fact, it is equal, x is equal greater or equal to minus 1 because you have this in the numerator. But because you divide here, we chose to what? To do what? We chose to multiply both the numerator and denominator by x plus 1. So we have to make sure that x plus 1 must be positive because this is the square root of x plus 1. And you end up with a form of this sort. You multiply both numerator and denominator. And since it exists now in the denominator, so it must be strictly greater than minus 1. Once you do this, in fact, you can move along. This resembles very much the square roots type of integration which we have encountered, we have met in our last lesson. You have to find either a kind of substitution or completing the square. Probably is going, I don't remember exactly in this slide, probably you have to complete the square, for example. In fact, yes, that's it. You have x plus 1 divided by x squared plus 3x plus 2. And here, yes, what we did here is, in fact, we realized that instead of completing the root first, the derivative of under the square root of x squared plus 3x is equal to 2x plus 3. So in fact, if we can put here 2x plus 3, you put it in the form which is amenable to substitution, because you remember the substitution, we said that there is a method in which if you find the integral in the form f of g of x times g prime of x, then the integral directly is capital F, which is the antiderivative of small f, and you form the composite function with g of x. So in fact, this is g of x, x3 x squared plus 3x plus 2, and this is g prime of x. So all you have to do is that if you divide by half, you multiply by half, and you in other words, if you divide by 2 and you multiply again by 2, you get here 2x plus 2. But the derivative of x squared plus 2x is 2x plus 3. So all you have to do, you add 3 and you subtract 1 to end up with 2. So again, now this form is what? Directly the integral of this f, which is 1 over the square root of x, this is f, and g, this is x squared plus 3x plus 2, and this is g prime. So directly the integral is equal to what? The integral is equal to square root of x squared plus 3x plus 2. This is the integral directly. Whether the other integrals, as I remember now, can be actually completed the square. If you complete the square here, then you end up with an integral which is known actually. This is the integral of what? This looks very much like cosine hyperbolic, inverse cosine hyperbolic, because you have, yes, in fact, this is it. And this inverse cosine, let's see what is look like. No, actually, I didn't calculate it, but let's calculate it. There is no problem. This is in fact cosine hyperbolic minus 1 of what? Of x plus 3 over 2 divided by half. That's it. Yes. So in fact, it is cosine hyperbolic minus 1 of 2x plus 3. So it must adhere, it must be compatible with the interval which we chose for x. So in fact, cosine minus 1 hyperbolic, this is the cosine hyperbolic, start from 1 as range. So actually the domain, we said the domain of the inverse function is the range of the function, of the original function. So this must look like this. Of course, this one has no inverse because it's not an injective function. You remember our first lessons. So it starts by 1 here. For example, we take this part, this branch here. So this is the cosine minus 1 hyperbolic. So in fact, you must have 2x plus 3 must be greater than what? Than 1. This gives you 2x greater than minus 2. As in fact, here it is. We recover the same condition for the previous integral, for the original integral, when we multiplied both numerator by and denominator by square root of x plus 1. So actually, this is your final result, and you add up. You don't ever forget the c added to the first expression here. So you have two expressions. One which is the square root, which you haven't been interested in calculating it till the end, but it's a square root, while the other one is cosine hyperbolic, inverse cosine hyperbolic of 2x plus 3. In fact, there are so many integrals, because actually, since we are ending our lessons of calculating antiderivative, it's no ending. Actually, there is no end to these kind of integrals. And in fact, there are books specialize only in obtaining antiderivatives, and the Russians actually, in fact, are very good at that because they have big books like this, and in these books, all you open it. There are no books for derivatives, in fact, because the student can do it easily. But there are books for antiderivatives because antiderivatives are very difficult to find. It needs experience, and some of them we cannot actually know beforehand whether it is in the form of elementary function or not. Like, for example, the integral of e to the x square or cosine x square. These form of integral, we don't know them. So in fact, we have to consult these books. It's like a dictionary, for example. So, but there are rules of thumb. In other words, there are traditions like this. In the form when you have, for example, integral of this sort, then this is in fact the substitution that you seek to use. You put, for example, x plus b is equal to 1 over u, and this works out your integral. Whereas, for example, if you have something of this sort, then what kind of substitution you would use? I would suppose u is equal, for example, to x. No, it's not true. I thought x power n plus b is equal to u. And in fact, if you put x to the power n 1 over u square, probably it might work better, etc. So in fact, you may start by assigning this to u, but in fact, this will work out better, etc. So in fact, these kind of substitution, they are obtained by experience, acquired by experience. Here, for example, you may take, this works out perfectly, x plus b is equal to u. Whereas here, for example, you have your substitution go this way, x plus b divided by x is equal to u. And thereon, etc. Here, for example, it's like actually the one which is under the square root. So this one is x to the power n, the one that I missed. I would suppose that, for example, this must be u, but in fact, if you put x to the power n is 1 over u, etc. So actually, these are acquired by experience. You have to perform many integrals until you acquire a certain experience by which one can anticipate the kind of substitution that will work out here and doesn't work, etc. Some work, some do not, but doesn't matter. These are difficult ones we are not interested in, but in fact they have to be said because these sometimes we meet them and the student have to try. There is no shame of trying many substitutions. I myself try. I'll try, for example, this one substitution. It doesn't work out, so I'll try the other substitution, etc. By this, actually, we have ended our lessons, our series of lessons concerning antiderivatives. And we said that you have to check them one by one. In other words, when you are given an integral to do, in the sense that you need to evaluate an indefinite integral, you need to calculate an antiderivative of function. You start, for example, by the simplest method, the substitution. And then if you find out that it's a product of two functions of different nature, then it is the integration by parts, directly like this. And then if it is only in the form of trigonometric integrals or hyperbolic integrals only, then you may use the kind of no substitution, but the kind of separation and decomposition until you can decompose your function into a function in which you use your substitution directly. And then when you have square roots, etc., then you may use trigonometric integral or hyperbolic integrals. This is how it goes. And finally, when you have rational functions of x, a polynomial of x divided by another polynomial of x, then you may transform it into a series of or partial fractions, a sum of partial fractions or a partial fraction expansion of your decomposition. I would suppose this is the word for it. You transform it into an addition of fractions which are called partial fractions, and you follow certain procedures that are actually systematic. And you have to make sure for a few things. One of very important thing is that you have to have the degree of the numerator must be smaller than the degree of the denominator. And otherwise, all you have to do is either you equate coefficients or you use the method of like I did, hiding, for example, a bracket, and then you substitute for the root of what is for the coefficient corresponding to the coefficient which you wish to calculate, which had as denominator x plus minus this root, etc. And this is how you do it. And finally, these methods are so numerous and the substitution are so numerous, and you have to do it yourself. You cannot. Nobody can teach you how to calculate antiderivatives. You have to check to choose one substitution, and then it doesn't work, and you choose another one, etc. Finally, after this series of lectures, I wish to remind you that this lecture, together with the other remaining ones, and the one which have proceeded, are all uploaded to the site of the MedNetU. which is the project administered by from Rome by Consortium Nettuno. For distance learning, and you may wish to subscribe to these lessons for the whether my lessons or the lessons of the remaining of the other professors, and until actually we meet in our next lecture concerning the definite integrals. Now I wish you good luck, and I thank you for your attention, and thank you very much.